Okay, so we're going to start looking at what's it mean to be a chemical bond, why do they bond, and how do they bond, okay? Big questions there. As James already pointed out, this is funny, a chemical bond, so there's no simple and complete way to define it, right? There's bonds that happen in a lot of different ways. But a bond is some sort of force that holds groups of atoms together, okay? And then makes that group of atoms function as a singular unit, okay? The reason there's no simple and complete way to define it is because there's multiple ways that atoms bond, right? Ionic bonds are trading of electrons and it creates a formal charge in which they hang out close together, right? And a covalent bond is a sharing of electrons, right? And an overlapping of those electron orbitals. So they behave a little bit differently. A bond will form if the energy combination is lower than that of separated atoms, right? So the whole goal for atoms is to get to the lowest energy level possible, right? Just like you guys. You want to be at your lowest energy all the time, right? Just like most people, okay? We want to be at our lowest energy. So their goal is to find the orientation of electrons in which gives them the lowest energy level possible. And if that happens to be in a bond, then that's how they go about. So here's the two hydrogen atoms. I don't know if these images printed on your notes or not. They did. Okay. Two hydrogen atoms. You'll see that if these two hydrogen atoms are too far apart, they don't have any interaction happening. When they start to come closer together, then they'll start to interact a little bit more, and as they come close together, that becomes what they consider the optimal distance, and that creates the lowest energy level possible. Okay, and so when they reach that optimum distance, then we'll see that bond form. Okay, so the graph of it here is on the next slide. What the bond length is and how what their energy levels are. If you look here at, let me turn this over. If you look up here, what's happening here? We're at a higher energy than normal. Do you see how this is different than this one? Yeah, they're too close together, right? They're crowded. Here they find their optimal distance because their energy level is negative, right? They're in the negative energy level, or negative potential energy, I'm sorry. And then here our distance is still far apart, but here we're even farther apart, so there's not much interaction taking place. So the whole goal is for those hydrogen atoms to reach their lowest energy level, right? Their optimum energy level. So, all right, let's go back now to key terms we've talked about before. Ionic bonding is always a transfer of electrons. Do we want to walk through what that looks like real quick? We talked about it in Chem 1, but do you want to look at it real quick, or do we already see that? Okay, so real quickly, I always use sodium and chloride as an example, all right? Sodium has how many valence electrons? 1. And how many valence electrons does chlorine have? 7. Okay, do we feel good about the trends with that? Yes. The group number trends. Okay, so now sodium, each of the atoms has a goal to have a complete octet, right? So sodium has a full octet underneath, right? Sodium's second energy level is full, but its third energy level only has 1 electron. So is it easier for sodium to gather 7 or to give away 1 and expose the full energy level below? Give away 1. And chlorine wants to collect 1 to fill its octet. So what happens is sodium says, sure, you can have it, okay? Transfers that electron to chlorine. When it does that, what charge does it leave sodium with? No, positive, right? That's right. Sodium leaves with positive. Chlorine is a negative. And what happens with positives and negatives?
They go together.
They attract, right? And so this attraction right here is so strong, this ionic attraction is so strong, that is considered a bond, right? There's no actual, interaction of their electrons because they've been traded. But that formal positive and formal negative are so strong, so strongly attracted that it's considered an ionic bond. Okay, does that make sense? Okay, very good. The second type is covalent bonding. That means they're shared equally by nuclei. Sometimes, what about if they're not equally shared? Do you remember what that word is?
Polar?
Yeah, if they're not shared equally, it's called a polar covalent bond. That's what we're going to look at next here. Okay, so what about intermediate cases? So ionic bonding means true give and take. Covalent bonding means true sharing, right? Evenly sharing. Where do you think we would see a perfectly shared covalent bond? I want you to think about this. Where would I see a covalent bond that is shared perfectly between the two atoms?
They're the same.
That's right. The same atom, particularly. So H to H would be a perfectly covalent bond, right? A perfectly nonpolar covalent bond. O to O, perfectly nonpolar covalent bond. Why is that?
Their nuclei are the exact same.
Okay, they have the same nucleic
And electrons.
radius, right? I can't think of the word I want to say, but they have the same radii. But okay, most importantly, I'm thinking they have the same electronegativity, right? They both want electrons as much as the other. So if we're thinking tug of war, they're both going to be pulling on those electrons with the same amount. Does that make sense? Is that coming back to us a little bit? That's what we're going to look next is at polar covalent bonds. If we see an uneven sharing of electrons between atoms, an uneven sharing of electrons, it results in the separation, the charge separation in a bond. So let's give an example of this here. Let's look at a bond between, I don't know, phosphorus and fluorine. Okay, I don't know what these numbers are, so I might not be picking a good example. Phosphorus and fluorine. Tell me what electronegativity is for fluorine.
4.0.
4.0, right? Which is the most electronegative atom on the whole table?
Fluorine.
Fluorine, right? Fluorine, phosphorus is 2.1. So that means that fluorine is more electronegative, which means the electrons within that bond, right? Let's simulate some electrons here. If these are where the electrons are supposed to sit, then that means in reality they're sitting here and maybe here, right? They're scooching toward fluorine a little bit more. So this would be considered a polar covalent bond. And when we draw a polar bond, we draw this little arrow. Do you remember what that arrow is called? A dipole. Yep, a dipole. A dipole moment. The dipole moment is the arrow itself. And then this creates a partial negative and a partial positive charge.
I think since Chem 1, I've been...
Yeah, dipole means two poles. And what do you know? What else do you know that has poles?
Bipoles.
Like a magnet, right? One side, one side. So dipole, yeah, means we've got two opposite ends. Okay, so when we talk about dipoles, we got to think about, well, one end of it's positive, one end of it's negative. You can have dipole moments within individual bonds, and you can have dipoles within full molecules. We're going to kind of look at both of those. This symbol right here stands for partial.
Okay.
It's like a Greek letter for delta. Okay, it's like a lowercase, probably technically a lowercase d, but it kind of looks like a s. Okay, but that's a lowercase delta. Why does fluorine get the partial negative?
Because it gets those extra electrons.
That's right. The electrons are closer to it, so it's a partial negative. It would not become a full negative charge until fluorine just like straight up takes that electron, right? It's not a full negative until there's a trading of electrons. So polar covalent bonds end up with this partial positive, partial negative charge happening. Okay, so polar means things are uneven. You might want to write that out, highlight it, whatever. But polar means uneven. Non-polar means even. Right? I think that's a little counterintuitive, but that's how it goes. Okay. So here's an example of all of these molecules here with a partial positive and partial negative. Okay, you'll see that version A is when they're not in an electric field. Okay, there's nothing that's pulling those electrons one way or the other. In diagram B, you see an electric field with a negative side and a positive side. So you see how all the molecules are oriented the same way, right? The partial positive is pointing toward the negative side. The partial negative is pointing toward the positive side, right? They align themselves because they've got that partial positive and partial negative. If the bonds were non-polar, then you would see no distinction between being in an electric field and not being in an electric field. Okay, they would look the same. All right, very good. All right, touching real quickly on electronegativity again. Electronegativity is the ability of an atom to attract shared electrons to itself. So that means electrons that are being shared currently, right, usually within a bond, if they're pulling them to themselves, that means it's got a high electronegativity. Okay, I would highlight this very bottom one. Fluorine is the most electronegative element. We've talked about that a couple different times, but that's just like a really kind of important key piece of information that we need to know. Okay, and then this middle one says for molecule HX, the relative electronegativities of H and X are determined by comparing the measured HX bond energy with the expected bond energy. Okay, so you can be looking at, not something that we're going to necessarily do, but you can measure what the energy is expected to be and what it actually is, and that'll give you the electronegativity values, right? The relative electronegativity values. That's kind of how these were determined, right? What were they supposed to be and what they actually were, and that allowed us to see that fluorine was always taking over electronegativity things. So there's a visual scale of the Pauling scale. Fluorine has a much higher electronegativity than francium. Let's talk about why. Why does francium have such a low electronegativity? Right? Think about valence electrons. Think about electron shells.
Because it only has one electron, and it would rather give it away than take.
Yeah, okay, it's only got one electron. That's a big part of it. What's the second part of it?
It has a bunch of full octets.
Bingo, right. It's that single electron is so far removed from the nucleus that like they don't really care. Right? And the nucleus isn't pulling on it as much, right? There's more protons there, but we're so far removed, right? We're in our 7th shell of electrons. So that one electron in the outermost shell, like no one cares, right? They don't care if it gets rid of it. So you'll see that that's pretty low. Okay?
Why don't some of like the noble gases have...
Noble gases aren't given electronegativity values because they won't take on electrons, right? Helium, neon, and argon specifically really won't take on electrons. After that, you get into, I shouldn't say won't want to, okay? After that, you get into the opening of the f orbitals, so they've got more space, so they could, but it's pretty unlikely that you would see that happen. But, it does every once in a while, but not enough that we would assign it a value. Okay, let's see this. If lithium and fluorine react, which has more attraction for electron? What does it have to be?
Fluorine.
Has to be fluorine, right? Why? Because it has more electronegativity values. It only needs 1 to complete its octet, and that shell is closest to the nucleus, okay? In a bond between chlorine and iodine, which has more attraction for the electron? Fluorine, okay? And why? It just has to deal with electronegativity values. Okay, very good. Does all this feel like it's still review from last year?
And
Good.
we had something where...
Okay, so here's some numbers you can put down for the range of polar covalent, non-polar covalent ionic bonds. Your Chem 1 textbook gives them a little differently, right? They're all in the same ballpark, but this is just a tiny bit different. 0 to 0.4 would be considered a non-polar. I'm going to write this up here, actually a non-polar covalent bond. Okay, then if we get into a shared electron range, we consider that polar covalent bond, and we get all the way to a trading range, we get an ionic bond. Okay, in Chem 1, the values were 0.3 to 1.7, so this just gives us a little more room to be nonpolar, but that's what those need to behave like, okay? There's also one other distinction that helps us determine if it's an ionic bond. What does ionic have to be between? A positive, negative, or a metal and a non-metal. That's a good clue for us that it's going to be an ionic bond already, right? You get some ionic bond tendencies if you go like metalloid and non-metal, right? You could maybe see it sharing so unevenly that you call it an ionic bond, but for the most part, it's going to be metal, non-metal. Metal, non-metal. All right. Oh, sorry. Do you have what you need on that one? Rank the following from most polar to least polar. Now you're going to rank the following bonds from most polar to least polar. Do you want to do the first one together, or you think you can do it? I think you can do it too.
It's like subtracting the bigger one.
That's right. That's right. And then we're going to put them in order.
Bigger number first?
Yes. Yep. Because you're really just looking for the difference. So we don't need it to come out negative. Right? Yep. That's what I had C to F, then N to F, then O to F. Yep.
I had,
Yeah.
I had the differences at 1.5, then 1, then 0.5.
oh, C, not CO. Okay.
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 All right. Very good. Which of the following bonds would be considered least polar, yet still be considered polar covalent? So I feel like you can automatically eliminate one. Right? We can automatically eliminate that one. Very good. Right? Because that would be a zero difference. Right? That would be completely non-polar. So we want it to be polar closest to the 0.4 range. Right? That's the goal. So Mg to O, I feel like we can get rid of that one too. Why do you think?
Because it's not close.
Because it's a metal and a non-metal, right? Metal and non-metal. So that's automatically, I feel like, a pretty big difference here. This would be 0.5. Silicon would be bigger than that. Carbon to oxygen is 1. So I feel like it's this guy, right?
Yep.
Okay, very good.
Yeah.
All right. Questions with any of those so far? Which of the following would be considered most polar without being considered ionic? Okay, so I feel like we can get rid of both of the same two that we just did, right? Because magnesium and oxygen are ionic. Oxygen is nonpolar. We get rid of this one because we just examined that was the least polar. And now we can just do the math. 1.0 and what's that going to be? 1.7? So I think it's that guy. Okay. Easy enough, right? All right. Dipole moment. This is when we're looking at distribution of electrons within a full molecule now. This is what we started looking at a little bit in our book yesterday, a day early. Dipole moment is when we see charge distribution that's uneven throughout the whole molecule. Okay, we use an arrow to represent the dipole moment. I think you guys probably remember this one. We point the arrow to the region, to the negative region, so we point them toward those electrons. The tail of the arrow indicates the positive region because we draw it like this with a little plus sign on the tail. Right, do you remember that part? We draw it with a little plus sign. Okay. Charge distribution can be represented by a region of positive charge and a region of negative charge.
This is such a dipole.
Here's water's image here. Okay, because if I was going to draw water, remember we've got two lone pairs happening up here. Plus the bonds within hydrogen and oxygen are more electronegative in oxygen's direction. So that's where the two partial negatives come from. Okay, but we see this area of the molecule that is negative and an area of the molecule that is positive, and so that's what's represented in this heat map here. Okay, so yesterday when we started looking at these by accident, we weren't sure what we were really looking at, right? But does it make sense now that one of those regions is really negative and one of those regions is the positive region?
Is the negative always red?
I think the negative is always red in this book. Yeah, in the images they're showing here, I think that's what they're looking at. Okay? The next one here is CO2. Okay? Here we do have polar covalent bonds, right? The bonds themselves are polar. But if we think about it in like terms of distribution of electrons, those end up canceling each other out. So carbon is a region of positive, but the oxygens on both sides balance each other out, and so we don't have one section of the molecule that is more polar than another. Okay, so that means this molecule would be non-polar. Do you see the difference? With polarity, we're really looking at asymmetry. Is there a region of the molecule that's more negative than another? Covalents are. Okay, covalents, when we each contribute an electron to a bond. Okay. And then ions. We already talked about this too. I gave the exact example. Wow, look at me. Okay. Sorry, did I skip something on the last slide that you need? Sorry. I just skipped it because we know. Okay. Two nonmetals sharing electrons, that is considered a covalent bond, right? when a nonmetal and a metal react, ions form so that valence configuration of the nonmetal achieves the electron configuration of the next noble gas atom. That's a really fancy way to say the nonmetal is getting a full octet and the metal is the one giving it away. Right? By achieving the noble gas configuration, that means it has 8 electrons. Right? So it's a really fancy way of saying the nonmetal, the chlorine in our example, is taking on that electron to have a full octet. Okay?
And the metal or the non-metal is giving away, right?
The metal gives it away because the metal is the one that will end up with the positive charge. Right? The metals are ones that have fewer valence electrons because they're on the left. All right, this next part I think is... Oh, sorry, James, go ahead.
For like number 57 through 70 on periodic table,
Uh-huh.
and like 89 through 102,
Mm-hmm.
where did they fall?
Yeah.
Almost done here. This next part is, I think, really interesting, but sometimes difficult for people to wrap their head around. But these are called isoelectronic series. And these are a series of atoms or ions that contain the same number of electrons. So let's look at these real quick. I want you to first, in the series, find the neutral one. Which one of these is neutral? Neon. And how many electrons does a neutral neon atom have?
10.
8. Where is it?
10 electrons total, not just valence,
Oh.
total. How many total does neon have?
It's the no gas.
I think 10, right? Neon's over there, any. And its atomic number is 10. So if it's neutral, my electrons will have to be 10 also. Now I'm going to look over here at fluorine. Fluorine is supposed to have how many electrons? Neutral fluorine would have 9. So if I have a negative charge, how many does it have? 10. If I have oxygen, neutral, it's supposed to have 8, but it's got a charge of negative 2. So how many does it have? 10, right? So every single ion listed in this series has 10 electrons. That's why they're called isoelectronic. Okay? All of these have 10 electrons. Aluminum, 10 electrons. Aluminum is supposed to have 13. But if aluminum has a +3 charge, that means I take away those 3 electrons. That leaves me with 10. Right? Simple enough, right?
What is the point with that?
Don't get me wrong, I just don't. I don't know what
All right. Choose an alkaline metal, an alkaline earth metal, a noble gas, and a halogen so that they constitute an isoelectronic series when metals and halogen are written in their most stable ions. So you're going to pick one. Okay, that sounds like a lot of big words, right? Just pick one. Pick a noble gas.
Okay.
Then pick an alkaline metal, group 1. Alkaline earth, group 2. Noble gas, and a halogen. Which one's halogen?
I wanted Krypton.
Valley.
Yeah, that's right, halogene. Okay?
Is that what you named her after?
Noble gas.
Noble gas is the last one. Halogen is
Funny.
fluorine's group.
Oh.
Okay, so you're going to pick 4. You're going to write the electron configuration for the series, because they're all going to have the same electron configuration, right? Because they all have the same numbers of electrons. Electron configuration, remember, is 1s2, 2s2. Yep. Okay, determine the number of electrons and the number of protons for each species. I want you to do that. You pick a noble gas, and you're going to do that. Okay, each on your own.
Have to pick.
Argon has how many electrons?
18.
18. So the next one in that series would be potassium.
Okay.
What would potassium's charge need to be to make it 18 electrons?
Plus 1.
Plus 1.
Oh, you just pick them in a row. Oh,
Yeah, they've got to be 4 in a row. There's no reason I would pick sodium because I would have to be sodium -7, right? That doesn't work.
Okay.
That doesn't have...
Do you
It's
have
not
to
like
configure each one? I thought
No, they're all going to have the same electron configuration because they all have the same number of electrons, right? 18 electrons. The next one in my series would be calcium, plus 2,
I see.
18 electrons. And my halogen would have to be chlorine, -1. They all have 18 electrons, right? Does that make sense? You're not just picking random ones. You want the series to go together. Okay?
Okay.
The difference is that they will still have their own numbers of protons, right? Because could each of these four elements have the same number of protons? No, because then that would mean they're the same element, right? Protons are that element's identity, so they cannot have that.